Okay, Bismillahirrahmanirrahim. Today we'll start from article number 7.8, piezoelectricity, uh, ferroelectricity, and the pyroelectricity. So let us start from the article number 7.8.1, pyroelectricity. So before starting this article, let me tell you one thing. So what is actually this pyroelectricity? So pyroelectricity is if you have two materials. After a few times, I will tell you what type of materials will be there, and we know there are some free electrons are there, and these free, not free electrons. That one is the surface electrons. So whenever we give some pressure, so from the mechanical point of view, so we know that if we give the pressure, then the uh, deformations will occur here, right? So when these deformations occurs, then there at the surface you will find uh, some free electrons, and these free electrons causes the flow of electricity. Okay. So look, certain crystal. So there are a few types of crystal. For example, quartz. That one is the crystalline silicon oxide. Then become polarized when they are mechanically stressed. That means whenever we will apply some mechanical uh, pressure, then uh, that one will sometimes is squeezed, or that means there will be some deformations. Okay. So then the charges appears on the surface of the crystal, and we will show these things in the figure also. So whenever there is the difference of the charges in the two surfaces of the crystal, then the electricity will flow. Okay. So look, if you look at this figure, say for example, if this one was our the crystal, that means the look, that one is the piezoelectric crystal with no applied stress or field. That means we have not applied any external electric field. So whenever we apply some forces, look, if we apply some forces on this material, then that material will experience a pressure, right? So that pressure will generate some free charges at the surface, so that there will be some difference of the charges the two surfaces. Okay. And this difference of these charges will generate some voltage, and that one is known as the piezoelectricity. Okay. So I think this is clear. Okay. So look, whenever we give the pressure in the downward, that means if the deformations occurs in this regard, then that will generate positive voltage, and if the deformations occurs in the uh, that means uh, that means in the upper side, or if the deformation is in the upper direction, then that one is negative voltage. It depends on the uh, distance in between the two surfaces. Okay. So look, this case will not occur for all the materials. So this one is occur for some special type of materials. So what are the those types of materials? So those types of materials are a few special type of materials. That means uh, we'll discuss these things. Look, if we apply the forces, then uh, the distance in from the center, or the center of mass of center will equal, and before the pressure, that one is also equal. Okay. So this one is the figure for sodium chloride. Okay. Now these things will occur. Look, that one is the center of symmetry. So we can describe the whole behavior of the examinations of the properties of unit cell, and that one is the center of summary. Okay. So if we look at the next figure, look, this one is an hexagonal crystal, and there we will have a center point. Okay. Now if we apply some pressure there, if we apply from the upward pressure, or if we apply from the two side pressures, then if you look carefully, then the center of this mass, or this center, is shifted. So whenever this center is shifted, only for those types of material, this piezoelectricity will occur. Okay. But if the pressure, if the center of this mass is not shifted, then this piezoelectricity will not occur there. Okay. Okay. uh, Now, suppose if the Tj is the applied mechanical stress along with j directions, then Pi is the induced polarizations along with I directions, then the true linearly related will be Pi equals to Dij and Tj. This one is known as piezoelectric effect. Okay, so this Dj is known as piezoelectric coefficients. Okay, and this one is an example of piezoelectric oscillator. Now, uh, this one is we need to know this electromechanical coupling factor. That means we have seen that there is a combinations of electrical energy and also the mechanical energy, and that one is described by a factor that one is known as K. So K square is the electrical energy converted to the mechanical energy divided by the input electrical energy. Okay, I forgot to mention another thing. Sometimes if we apply the external electric field to the these piezoelectric materials, that means if we apply the electric field to these sort of materials, then these deformations will occur or this mechanical deformations will occur. So these again this type of conversions is also known as piezoelectric effect. Okay. Uh, so if that is the K electromechanical coupling factor, that the electrical energy converted to the mechanical energy divided by input of the electrical energy. Or we can also say that if that one is the reverse way, that one is mechanical energy converted to the electrical energy divided by the input mechanical energy. Okay. Both the thing is known as electromechanical coupling factor. Okay. So here we will learn one thing, that one is the PZT. This PZT is known as zirconate titanium. Uh, yeah, zirconate titanium. Okay. So here you will find the effect of these eggs. That means the deformation. That means the uh, what I can say. That is the deformations of this uh, combinations of this material or something like this. Then the pipe, this example 7.1, this one is also very important. That one is the piezoelectric spark generator. So please try to go through that things, and that one is very important, and also this mathematical things. So look, this one is the piezoelectric effect. Here we have, there is a combination of two piezoelectric uh, materials, and the piezoelectric voltage coefficients. Please go through these things. These things is very important. Okay. Next thing is article number 7.8.2. That one is the piezoelectricity. That one is the quartz oscillator or the filters. So from the mechanical or the from the simple harmonic motions, you know about the resonance, and that one is sometimes known as mechanical resonance, or sometimes that one is the mechanical standing wave. So the n lambda divided by 2 is equals to L. So we can describe this quartz in terms of an inductor and a capacitor and also a series resistor. Okay, so we know that from the simple harmonic motions or from the oscillator, that sometimes that one will store energy and sometimes that one will release energy, and that one will move something like a simple pendulum. Okay. And we know about the resonant frequency. The mechanical resonant frequency Fs is described as 1 divided by 2 s pi root over Lc, where this L and the C is the two equivalent capacitance and also the inductance. Similarly, whenever there is another thing which one is known as anti-resonant frequency, that one is Fa, which can be expressed in terms of 1 divided by 2 pi root over LC prime. The value of this inductor is fixed for the both the cases, but the value of the capacitor is different. Where this LC or the C prime is defined as 1 by C prime equals to 1 by C naught plus 1 by C. So you know about the quality factor and this sort of thing. So next, the example number 7.14, which one is also very important. So yeah, there is a also a derivations and also mathematical things. That one is you have to prove that from the that means from electric coupling coefficients of the electrocoupling factor, you know that K square equals to mechanical energy stored divided by the total energy stored. And they asked you to prove that K square equals to 1 minus Fs divided by Fa square. So what is Fs? So Fs equals to that the resonant frequency, mechanical resonant frequency 1 divided by 2 pi root over LC, and Fa equals to 1 divided by 2 pi root over LC prime. So this I think all of you should solve these things because these things is very important for the exam. I may ask these things. So please try to solve this thing. And this one is very easy to solve. You have to go something like reverse way. So here they have skipped few lines, around 3 to 4 lines. That one is K squared, that the mechanical energy stored equals to, we know that the mechanical energy equals to half CV square, and the total energy equals to half CV square plus half C naught V square. Then both the capacitance and the half will be cancelled each other. So both the voltage and the half factors will cancel from the numerator and also the denominator. So C divided by C plus C naught. Okay. Now these terms you have to prove from the previous equations to this part. Okay, this one is very important. So it takes around 3 to 4 or 4 to 5 lines to prove these things. So you can also divide. You can also look here. There is in the denominator there is a plus sign, but here there is a minus sign. So I'm giving you some hints. So that one is you have to add a C naught minus C naught divided by C plus C naught, which one will give you the factor 1 for from the left side, and there will be another minus terms. So if you work with that minus terms, so that one will give you this right side part. Okay. So after that, rearranging the equations, try to solve the mathematical problems here. Okay. Next, there will be another examples. That one is 7.15, which one is also very important. Uh, so that one is that one depends on the quality factors. So you have to find out the value of the capacitance and also the inductance from the crystal. So same formula, just use the formula. Okay. Now we move to the article number 7.8.3. That one is the ferroelectric and the pyroelectric crystal. So similarly, there will be some polarizations. So in the polarization factor, there will be positive charges and the negative charges in the crystal, which one is known as the ferroelectricity. That one is the barium titanate. That one is uh, in. So look, so whenever we you have to learn one thing beforehand. That one is what is called sintering. So what is called sintering? So say for example, I have a crystal say for example that one is a crystal of sodium chloride. Okay. So or I have a crystal of say for example zinc ferrite or something like that. Okay. So try to find if you say for example if you take the measurement of the IV characteristics or blah 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 different characterizations. You have completed all the characterizations for that sample. After that, whenever you heat it up, that means if you sintered means you keep that crystal for a certain temperature. Say for example that one is at 2000 Kelvin. So whenever the crystal is at 2000 Kelvin, there will be deformations in the inner side. Okay, so if there is a deformation in the inner cell, then the properties will also uh, the properties will also change. So these type of things, that means the sintering purpose is here. So you know about the Curie temperature. So whenever that one is, you crosses that temperature, then this delta P, that one is the polarizations. That means uh, 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 there will be shifting of this polarization, and due to that purpose, there will be some flow of electricity, and that is known as the ferroelectricity. Okay, and now this terminology P is equals to epsilon naught into epsilon r minus 1 multiplied with the electric field E. Now, next one is the delta P, that one is the amount of change of the polarizations. So, only the terminology changed here is uh, delta P is associated with delta E. So, we have derived this polarizations expression beforehand. Okay. So previously that one is due to the pressures, that means the mechanical stress. That one is known as the piezoelectricity. Now, if we apply the heat, that means if we apply the heat, then there will be movement of the surface electrons or something else. That means there will be some difference of the charges there. So that one is known as the ferroelectricity. Okay, that the pyroelectricity coefficient is defined as P equals to delta P divided by delta T. And related to this, you have to also solve some mathematical problems. Please try to solve. And uh, they have discussed about the curves. So for the exam, these curves are not so important, but the mathematical problems and the basic understanding is important. Okay, so. So this one is the induced polarization current density. Which one is, you know about the current density, and this one is known as the photoelectric current density. And this there is a terms, that one is the current responsivity. That means the response of the current is denoted by the symbol Ri. That means the photoelectric current divided by the input radiation power. Okay, and we know that the P equals to Vi or from this formula. And next one is the pyroelectric voltage responsibility, that one is denoted by RV. And these sort of things. Next, try to solve the example number 7.16. And the initial part there is a derivations, and the next part there is a mathematical part. Okay, so these derivations is also important. This derivations part is also important. Okay, so this is all about this piezoelectricity, ferroelectricity, and the pyroelectricity. Okay, now I have shown you everything from the book. Now move to the lecture note of the Bruet professor. Okay, so you will find that lecture note number is 22. Okay, so at the very beginning he has discussed about the, so in the, if you just go through this part, then you will find the summary. Okay, so I will add it two lecture notes. The first part will be the from the book, and I am uploading the next lecture. That one is from the Board professor. Okay,